Hello everyone, welcome to 3D Thinker. Today we're going to discuss something what I think is very interesting. With just a small amount of data, it is amazing how you can infer a lot of information if you can make the correct assumptions. And nothing says that better than the case we have today, which is what happened to the Titan submersible. I have a theory based on the transcripts that were released several days ago. I'm not sure if they've been confirmed to be correct yet or not, but I'm just going to go for now on the assumption that they are valid and that they are not a hoax of some kind. And based on those transcripts, I'm going to walk through a series of steps and just a few basic calculations to infer what might have been the sequence of events leading up to the Titan's ultimate implosion. We're going to start with this. What I've taken is the transcripts from another YouTube video I saw, and I've extracted and copied on paper only those comments of the communication from the submarine to the polar prints and what time they happen. And I've extracted only those that basically have what I consider critical information for this analysis. So we're going to begin. What I've got in the left column is the comms, and these are all transmissions from the Titan to the polar prints. And on the dual column on the right, I've got the timing. I've got the timestamp on the left and number of minutes between relevant transmissions on the right. And I've taken the minutes to decimal point for later calculations. So we'll start with this. In part one, we're just going to go over the sequence of events. Then part two, which will be in the same video, and part three, we'll do a series of calculations. So the abbreviated text are here. We're going to ignore this line for now. This will show up later in the calculations. All this shows is that during prior descents to the Titanic, it would take about 2.5 hours or 150 minutes. Now, we'll begin with 07:54:07. 7 in the morning, I'll use metric time, 54 minutes and 7 seconds. The Titan submersible communicated descending now. Where I have in quotes is a direct quote. Where I don't have quotes, it's just a summary in my own words. So they began their descent 07:54:07. Then the next relevant transmission was a system check and a depth check, and that was at 08:21:28. That was, I'm going to call that plus 27 minutes, 0.35, plus 27.35 minutes. The next is another system check and a depth check. That was at 08:51:30, and that's another 30.03 minutes from the prior check. Then they sent another transmission at 09:17:50, basically saying everything is okay, and they gave another depth report. That was 26.33 minutes after the immediately prior transmission. It was at 09:28:16 that the first signs of trouble showed, when part of their transmission included alarm from the RTM. RTM meaning the real-time monitoring system, which is the acoustic system that was designed to detect any failure, cracking, micro-cracking of the carbon fiber cylindrical body that is between the two titanium hemispherical ends of the pressure chamber. Very shortly after that, only 19 seconds later, it appears that Stockton Rush had noticed that the rate of descent was fast, and he transmitted reducing velocity, descent, depth 3433. And then only about 2 minutes later, he transmits no change with thrust, descent increasing at 35, to which he must be saying at 3,500 meters roughly, release ballast now. So at this point, at 09:30:36, he cut loose those ballast pipes that hang off the bottom of the submersible. Shortly after that, about 2 minutes later, he says no improvement, preparing to jettison the frame. So at this point, he knows something's truly wrong, because despite cutting loose the ballast, they are continuing to descend. About 3 minutes later, he says, frame jettisoned, starting ascent now. So now that he's dropped both the ballast and the frame, it looks like he has determined that the submersible is beginning to now lose depth or rise vertically instead of descending. So it's beginning to ascend, although we don't yet know the rate. About 3 minutes later, 2.5 minutes, he reports cracking sound aft. Then about 4 minutes later, he transmits ascending now, very slow, global RTM alert active, all red. So from what I understand, he has a series of between 20 and 30 pickups located at different positions around the carbon fiber frame. And when any one of them detects any kind of acoustic indication, microscopic noise, it goes red. It's an LED, I believe. And apparently all of them are now red. So all of them have displayed a small noise of some kind. About 1.5 minutes later, he transmits, so it's at 09:43:42, ascent, quarter predicted, unclear why, no indicator. I'm not sure what no indicator means. And he says at 3476, so he's at a depth of 3476 meters. No indicator may mean that he no longer has an indication of the vertical thruster, because earlier here at 09:30, he said no change with thrust. So it means that at 09:30:36, he activated the vertical thruster, but did not notice a significant change in the rate of descent. Here he says no indicator at 3476. So I don't know if that's implying that his thruster stopped, and that may be confirmed by the next entry, which is also their last. At 09:45:37, he transmits red on A power bus, switched to B. At 3457 meters, more sounds aft. And that was the last transmission from the Titan to the Polar Prince. All other transmissions are from the Polar Prince to the Titan, asking for status, but not getting any response. So it looks like from 09:43:42 to 09:45:37, just a little bit under 2 minutes, they only ascended by about 19 meters, which is very slow, as you will see. Okay, that's the end of part 1. I'm going to open my chart and switch to part 2, which is where the calculations get interesting. Okay, part 2 is now where I'm tracking the depth and rate of descent of the Titan submersible relative to the timestamps we discussed before. So what I've got in the next columns are as follows. So we've got, again, the comms here, the timestamp. This is the amount of time that's gone by between each successive row or event. And now we've got here the depth as called out by the Titan submersible at the different times. I've calculated pressure in atmospheres, pressure above atmospheric pressure, so 0 would be at sea level. I'm not counting the atmospheric pressure on top of it. We've got delta depth, change of depth, again, between different timestamps. Then we've got ROD, which I'm calling rate of descent. Really, it's just your vertical downward velocity averaged out. But that is our rate of descent in meters per minute. And beside it, I've got it meters per second, which will be used in a subsequent calculation. And the last column I've got is relative to normal. So normal is what I'm defining as the other times the submersible descended. So we've got here summary of prior descents to the Titanic. They went 3,800 meters down in 150 minutes. So that turns out to be a rate of descent of about 25.3 meters per minute, or about just under half a meter per second. Now I'm calling that 1.00. All the other rates of descent are going to be relative to this number, as you will see. So at the first timestamp, descending now, that's our 0 mark. Everything else is 0. The first system check and depth check is at 0 plus 27.35 minutes, to which they've achieved a depth of 756 meters. That's 75 atmospheres of static pressure. The change is they've gone plus 756 meters from 0. The rate of descent is 27.6, or 0.46 meters per second. That is about almost 10% faster than normal. It's 1.09 times as fast as their prior rates of descent. So they're descending a little bit quicker, and I'm sure at this point, even if anyone noted that, that will not have brought up any red flags, since it's in the single digits, the percentage increase. Their next system check and depth check was at 08:51:30. Now another 30.03 minutes has passed since the last check. They've achieved 1,934 meters, or a pressure of 193 atmospheres. They have descended an additional 1,178 meters from the last check. And over that period of time, that works out to a descent rate of this period of 39.2 meters per minute, or 0.65 meters per second. This is now about 55% faster than prior descents to the Titanic. Now we've got another AOK and a depth check at 09:17:50. At this point, another 26.33 minutes has passed. The depth is 2960, pressure of 295 atmospheres. They have descended an additional 1,026 meters from the last depth check. And divide that by the amount of time, and we've got now 39 meters per minute. So it's actually hasn't changed really. In fact, it seems to have been a little bit less. Mind you, when he's called out the depths, for example, he may have looked at the depth and then at the end he added the depth in his transmission, and so the depth may have changed by some meters during that time. But essentially, the rate of descent is the same, about 0.65 meters per second, 2/3 of a meter per second, or 2 feet per second. And just because my spreadsheet has this, it's 1.54 times. So it's still about 55% faster than normal. This timestamp, he did not call it a depth. This is just the indication when the real-time monitoring went into red. The next timestamp, 09:28:35, another 10.75 minutes has passed since the last depth check, when he states he's at 3,433 meters. That's a pressure of 342 atmospheres. And at this point, they have descended an additional 473 meters in just under 11 minutes. That gives us a rate of descent of now 44 meters per minute, or nearly 3/4 of a meter per second. They are now about 1.74 times the original rate of descent. So 1 3/4, they're close to going twice as fast as they have on all the previous dives. And 2 minutes later, when he tried to turn on the thrust to slow down the descent, he said the descent rate is still increasing, or maybe he just noticed it now. He says he's at 35, Now that could mean 3,500, it could mean 3,520, 3,510. What I did was I set it to approximately 3,522 because the rate of descent should not have changed that much within a span of only 2 more minutes, and this keeps the numbers looking normal. In other words, if you had the same rate of descent at this exact time, he should have been at 3,522. In other words, he would have gained another 89 meters in about 2 minutes. And again, because the rate of descent I've made it the same, we still have the same number. So what we see is they start off descending within the first 27 minutes at just a little under 10% faster than normal. And then over the next half hour, that increased to over 50% faster than normal. And then about an hour later, they're now 75% faster than normal, roughly. Now, during these times, he did not provide any depths at these timestamps, which is why I've got an arrow just going here, just like here. So any time changes are now from this point to this point. When they finally begin to ascend, this is after dropping the ballast, turning on or attempting to turn on the thrusters, dropping the ballast, and jettisoning the frame. At this point, he says, ascent, quarter predicted, unclear why, no indicator. So at this time, about another 13.1 minutes have passed since the 3,522 mark. Now, clearly they are ascending because they're now at 3,476. So they've actually rose by about 46 meters in a time span of about 13 minutes. So they're rising, but the rate of rise is extremely slow. It's only 3.5 meters per minute. That's extremely slow. That's about less than 1/10 what the rate of descent was here. That's basically just over, you've got roughly about 1 story in 1 minute, about 10, 11 feet. And then now I don't know, I'm suspecting that at some point either this thruster did not start, which is why he said no indicator, or it started but then stopped because the A power bus went out. Then he starts B power bus, or switches to B. At this point he calls he's at 3,457. So at that point, between this point and this point, just under 2 minutes has gone by, and he has gained some ascent. He went up only 19 meters, but that was in just under 2 minutes. So at this point, he's ascending at nearly 10 meters per minute. Prior to that, they were ascending at only 3.5 meters per minute. And I'm going to just assume for now that the thrusters either worked for a very short period of time, or they did not come on at all until he realized it and switched to power bus B. At that point, they're starting to rise at still a slow rate, but at least nearly triple what it was before. So we have a general trend that the deeper they go, in general, the faster the descent. And when they're trying to ascend, it is slower than they expected. One minor thing, I don't really know how the rate of descent was not increasing here, but we're going to talk about that a little bit later. For now, we'll just let the math speak for itself. And we see here we've got 109. Then over a period of about an hour, they're about 55% faster. And over a period of about, let's say, another 40 minutes or so, 45 minutes, they sped up to about 1.74 times as fast. Okay, that concludes part 2. I'm going to turn the page over and we'll continue on part 3, where we've got additional calculations that can actually at least quantify to some degree what may be happening. Okay, here in part 3, I've now extended the calculations to what you can see is here, drag force versus net weight. So one of the theories is, it's not just my theory, that the sub began to take on water. That through some combination of either micro cracks in the existing structure or at the ends where the carbon fiber body was glued onto the titanium ring, or at the joint where the titanium hemisphere, either on the aft side or the forward side, is bolted to the titanium ring, somewhere water could be seeping in. And where it might be seeping in, we can possibly infer from the data of part 4. But for now, we're going to just quantify the leakage rate. And how we're going to do it is we're going to estimate what is the change of weight, the total weight of the submersible with all its occupants, as everything is progressing. So what we've got here is we have rates of descent. Now, if we can approximate the submersible as basically a cylinder, it does have spherical ends, but if we're going to do just a general, simple calculation, I'm going to take a length of roughly 6 meters, even though it's something like 6.7 or more. If you go tip of the tail fin of the aft side to the viewing port on the forward side. And I'm going to just call that a cylinder, and I'm going to give it a cross-sectional area based on its diameter times the effective length. And as that cylinder is plowing through salt water, it's doing so under gravity acting upon a net weight. And the net weight is going to be the gross weight of the vehicle minus any effect of buoyancy, i.e. the airspace inside and anything else that could be adding buoyancy to it. That's probably the major part. And so we will actually be able to roughly infer the net weight of the entire submersible in the following manner. If we look here, we've got the drag equation. It's fairly well known in fluid mechanics, where you have the force of drag equals the drag coefficient C sub D times AC, the cross-sectional area, times 1/2 times the density of the medium times velocity squared. In our case, velocity is rate of descent. The coefficient of drag is going to be a function of shape and Reynolds number. And Reynolds number is just a fluid mechanical dimensionless quantity, which is density times velocity times diameter divided by viscosity of the fluid. I've looked these values up, and we've got density of seawater. It varies a little bit as you go deeper. As the pressure increases, water is very slightly compressible. I'm just going to go with an average of 1030 kilograms per cubic meter. The dynamic viscosity of seawater at around 12 degrees Celsius is 1.3 times 10 to the minus 3 Pascal seconds. Everything is in metric units because it makes things very much easier to calculate. It's about 30% more viscous than if the water was at 20 degrees Celsius, or what would be considered room temperature. But since the water is cold, and because they were descending to a depth which is even colder, 12 degrees I think is a reasonable assumption. And then we've got, of course, gravitational acceleration, which we need to back out a weight from the force. That's 9.8065 meters per second squared. So in order to get the drag, you need to have the drag coefficient. The drag coefficient is a function of Reynolds number, which is basically a function of geometry and velocity. So I've included velocity here as rate of descent in meters per second. That's why it's there converted. So in this next sequence of columns, we've got Reynolds number, which I've calculated based on this formula. This density times rate of descent times the OD of the shell, and that's what's giving drag, so I'm using the OD as given as 2.5 meters. Divided by the viscosity, which we're going to assume is going to stay roughly constant. So we've got Reynolds number. This is for a typical descent, going at 0.42 meters per second. We've got Reynolds number for their initial part of their descent, which was a little bit faster, 910,000. And we've got Reynolds number for 0.65 meters per second, which is 1.3 million. And then for the latter part of their descent is at 0.73, 0.74 meters per second. It's about 1.5 million. Again, it's a dimensionless number. But if you refer to any graphs, and there's many of them on search engines you can find, it shows a cylinder in cross flow, what the drag coefficient is, and the drag coefficient is another dimensionless quantity. The drag coefficient is the next column, and so I convert from Reynolds number for a cylinder in cross flow. In other words, the cylinder is going not end forward, but sideways downwards. So we've got a drag coefficient during a typical descent of 0.35, and of course, as velocity increases in this part of the relationship between cylinder drag and Reynolds number, it actually rises slightly as Reynolds number goes up, as velocity goes up. So it goes up to 0.4, 0.42, and then 0.45. And then here I've calculated the force in newtons of drag. In other words, this is the drag force exerted on that roughly cylindrical shape as it is sinking through seawater at these speeds. So in a typical descent, the force in newtons is around 482. Now, since most people can't think, or at least have an intuitive feel for what newtons are, I'm going to divide that by g. So according to this part of the equation, if you take force divided by gravitational acceleration, this gives you your buoyant effective weight, what I'm calling WEFF. So effective weight is this number divided by 9.8065 meters per second squared. So that converts newtons to kilograms of weight. So on a typical descent, they would have a drag force of 482 newtons, which is about 49 kilograms of effective weight. So that means if you took 49 kilograms, a shape that weighed that much, had it as a cylinder that was roughly 15 square meters of frontal area, or cross-sectional area, you should get a velocity of about 0.4 meters per second. So now what we're going to do is we're going to do that on every line, and you're going to see as the velocity increases with the area remaining the same, that implies that it's beginning to weigh more. In other words, the submarine is beginning to become heavier. And what makes sense that it's becoming heavier is that it is taking on water. There's no other way it can get heavier once it's underwater. No weight can be added. Nothing is going to become more massive while it's there. They're certainly not going to be able to shed any weight until they specifically drop ballast. And so any increase in velocity must mean that there's an increase of effective weight. And that translates kilo for kilo as total weight. So when we start, or when they start their descent, they have at a 0.46 velocity, that translates into a drag force of 656 newtons, which is 67 kilograms. That's 18 kilograms more, or roughly 17 liters more weight of water. That is what's implied here. Then about a half hour later, they're moving at 0.65 meters per second. At the correct drag coefficient, we've got a force in newtons of around 1387, which translates to an effective weight of 141. That's 92 more than what it would have been under normal circumstances. And what that means is that they've gained 17 liters of water plus another 72 liters of water. So 90-something liters is about 22 gallons, roughly. It's about just under 4 liters is in a U.S. gallon. Here, because the drag force is essentially unchanged, we're going to leave that out. That could mean several things. It could mean, for example, that there was a leakage and one closed up as the pressure pressed on a micro crack that had a leakage route, but then another leakage point may have opened, or the one that opened was very small, so it briefly sealed. We don't know exactly when these numbers were called out, but I don't think that will make a huge difference. But it seems to indicate that it's gained a weight of water, but then gained nothing during this 26 minutes. However, then it continues. And then when we get to 0928, they are now the equivalent of 141 kilograms more than what they would be under normal circumstances, which is an additional 50 liters of seawater. The next one's only 2 minutes longer, and because we don't have an exact value of depth, I just put that number in to keep the descent rate the same. We're just going to ignore that. But what we've got here is we've now got them taking on about 141 kilograms of seawater, which is close to that amount of liters, since every liter of seawater is 1.03 kilograms. And what you'll notice is that as we go to the next page, we're going to look at what the leakage rate is. We're going to look at how much has leaked in, presumably, and we're going to divide by the amount of time, and then we're going to see if those numbers actually make sense. So we're now going to go to part 4, and this is the end of part 3. All right, so now we're at part 4, and now I've added several columns to the right of the spreadsheet. What I'm doing now is I'm taking the presumed amounts of water that have ingressed into the crew compartment of the submersible. We've got 3 main periods of calculated in leakage. The first is the period from 7:54 to 8:21, the first part of the descent, the first almost half hour. Then the next half hour of 8:21 to 8:51, and then we've got an amount that is approximately another nearly 11 minutes. And we've got basically roughly 17 liters of seawater that came in over a period of 27 minutes, about 0.6 liters per minute. Then we've got 72 liters over roughly half an hour, so that gives about 2.4 liters per minute. And then towards the end at 9:28, we've got about 50 liters over a period of only 11 minutes, so that increases the leak rate to around 4.6 liters per minute. For those of you familiar with gallons, U.S. gallons about 3.78 liters, so this is about 1.25 gallons per minute. This is just over, let's say, between over half and less than 2/3, and this is a pretty small amount. What I've also done is, now the reason this is increasing is because their depth is increasing, and higher depth comes higher pressure. So what I've done here, this second column, is since the pressure is growing in a linear sense as they increase depth, and this is a reflection of how much it's increased over a period of time, I'm taking the average pressure from the period before to the period of. So what we've got here is, for example, the period of the leakage being on average of about 0.6 liters per minute, their pressure was an average of 0 to 75. So I've just taken the arithmetic average, the starting pressure, the finishing pressure divided by 2, since it will be a roughly linear progression. Likewise, from 75 to 193, that's an average external pressure of 134 atmospheres. And finally, from this last period, we've got pressure from 295 to 342, giving an average of approximately 319 atmospheres, during which that leakage was about 4.6 liters per minute. And then the next column I've added is, I want to see if this is making sense, first of all, if the leakage rate is consistent for the pressure. And second of all, if it is consistent, that's going to indicate that the leakage area, whatever leakage path is there, it's going to have some thickness, if you will, or gap. It'll have a width, and it'll have probably some length to where it communicates to the outside. If the leakage is consistent over these 3 periods, what it means is that leakage path hasn't really changed. So what this third column is the flow rate, liters per minute, divided by the average pressure drop, or delta P, of 100 atmosphere increments. So this column is basically the flow over the delta P per 100 atmospheres. So in this case, we got 0.6 liters per minute divided by 0.38 100 atmosphere units. The number is a little bit easier, otherwise it would be 0.0167. So basically this is liters per minute for every 100 atmospheres of dP. So we've got 1.67 in the early part of the leakage, the first half hour of the dive. It goes up slightly to about 1.80 during the second half hour of the dive. And in that 10-minute interval, or 11-minute interval we looked at, it's about 1.45. Now, these numbers are very sensitive to the calculations that come before, but despite that, it's pretty consistent. The average is about 1.64, so this first value is pretty much on the average, and it's basically that plus or minus 0.13, and that's, or 0.15, let's say. So that's pretty much this plus or minus 10%. So a variation of plus or minus 10%, given how rough these calculations are, is, for me, pretty consistent. What this is also showing, what's referred to as the resistance to flow, is the inverse of this. The resistance is how much pressure you need for a given flow. This is more how much flow you're getting for a given pressure. But the resistance, since it's simply 1 over these numbers, is also going to be pretty consistent. So if the flow resistance isn't changing by much, that implies to me that the flow path is pretty much unchanged during this period. This last column is simply, it's an indication of, assuming this leakage rate is correct and everything is true and that this transcript is true, this is how much time they would have had at any given elevation before the crew compartment of the submarine would be flooded with seawater. It's a bit of a morbid number, but it's one that will at least tell us when they might have reached the point of no return, and you will see what I mean by that. So what I did was I took the dimensions, the inner dimensions of the crew space, again off the various sources on the internet. ID is about, that's inner diameter, 1.68 meters. That's a radius of 0.84. The section that's a cylinder, that was the titanium spool wound with carbon fiber. It's about 2.5 meters in length, 2.54. So the internal volume is going to be the sum of the cylindrical section plus 2 hemispherical sections, which is basically another sphere. So if we take the cylinder section, is basically the volume is pi r squared times L. The volume of the 2 hemispheres together is an additional 4/3 pi r cubed. You get a volume of 5.63 plus 2.483, a total of 8.113 cubic meters, which is about 8,113 liters. I have not subtracted from this amount other things that take up space in the crew compartment, such as the 5 crew members themselves, the platform they're sitting on, the equipment and wiring. But again, this is just a general sense, a rough calculation to show what would be happening and roughly how much time they would have with these conditions. So if I take 0.6 liters per minute and divide that into the volume of 8,113 liters, just over 8,000 liters, you get about 215 hours. This is time in hours, not minutes. So if they had realized they had water ingress in that first half hour of the dive, they had plenty of time to A, not accumulate too much water weight, and B, to drop ballast, drop the frame if necessary, activate the vertical thrusters, and resurface. In the second half hour, you can see that amount of time drops dramatically. They've already picked up some weight. Again, the earlier part, they only picked up maybe 18 kilograms, which isn't very much. That's 18 liters, or maybe roughly, we can say 4 gallons, 4.5 gallons. By the time they were in the second half hour, they picked up 92 kilograms total. That's an additional 72 liters from the original 17. That's pretty much the weight of another big person. So at this point, they've already accumulated extra weight. And at that point, the leakage rate being 2.4 liters per minute, they would have had 56 hours before the internal crew compartment would have been mostly flooded with seawater. Now, since they're able to ascend when they were further down, when the situation was even worse, I'm thinking that they could have, at this point, even been able to surface. The amount of weight being under 100 kilograms, I believe dropping the ballast, and if they had to, dropping the frame, they could have easily ascended from a depth of around 2,000 within 56 hours. However, when they're down at around 3,400 or 3,500 meters of depth, the situation changes quite a bit. You can see now that they've accumulated a total of 143 kilograms. That's like 2 more average-sized people than what normally would have been down there. And on top of that, their rate of in-leakage is 4.6 liters per minute. At that point, they've only got 29 hours before the entire space inside the sub is going to essentially flood. On top of that, as we saw, their rate of ascent with both vertical thrusters was just under 10 meters per minute. That would be 345 minutes, but that's assuming they could sustain that. At this ingress rate, you're basically adding another 4.5 kilograms per minute, just over 4.6 per minute. So as the minutes tick away, even if they had the vertical thrusters and did not implode, this number would have been dropping off rapidly. There's no way they could have surfaced in the amount of time they had left. Again, as mentioned before, they may not have had enough battery life to take over 300 hours that amount of time to get back to the surface. 345 minutes or so. And again, it would have taken longer because the ascent rate would have essentially stalled at one point, and they would have started to sink again once the amount of water taken on exceeded the capability of the thrusters to raise them. In other words, their net weight would have been too much at that point, and they simply would have sank back down, and then it just would have been a matter of time as the seawater seeped in. So bottom line is, even had they not imploded, they had less than 30 hours before they essentially would have asphyxiated or drowned. I recall that from the first time the submersible went without communication, several days had already gone by and the search hadn't found anything. So there could be some arguments made, well, that leakage, would have pressurized the air inside, and as the air pressure built up, it would have resisted it. But at the pressure they're at, which is about 350 atmospheres, what that means is that the volume of air would have been reduced to 1/350th of what it was before any leaks started, when they were at atmospheric pressure inside the submersible. That would have left maybe a very small pocket of air at the very top of that cylinder where they'd have to be stretching up to breathe it. Even if the oxygen continued to pour in, even if the CO2 system had been flooded out, essentially what would have happened is the CO2 in that pocket would have built up for their respiration. Even if there was enough oxygen coming in, they would have been poisoned by the CO2 concentration as it built up. And even at some point the oxygen would have run out. They said they had 96 minutes. How much would that have truly been when the pressure inside is now increasing as the seawater is compressing that airspace? Plus, we don't know if an additional crack appeared somewhere on the top side, that air pocket would have leaked out. In other words, if the cracking they heard continued and another leak path opened up, then that air inside could quickly have been purged to the outside, and there would have been no air pocket left. So bottom line is, they pretty much had several fates at this point, what I'm calling the point of no return, which is they either would have frozen to death, being immersed in extremely cold water with no heat source, well before that pocket of air was compressed. At that point, they would have, if they'd not been dead already, they would have asphyxiated or been poisoned by CO2. And on top of all that, if that air pocket had been purged away through another crack, they would have simply drowned. So all things considered, the fact that the sub had imploded shortly after this time was probably a blessing for them, because at least the end was quick and painless. I'm going to now show one last note of interest. Again, it's incredible that by knowing simply the time and depth, we can infer things like pressure, rate of descent. We can calculate out an equivalent effective weight, for which we can calculate the added weight due to water ingress. From that, we can calculate a leakage rate. We can even from that calculate what would have been the likely size of the leakage path that was generating that leak rate. I'd mentioned earlier I had a feeling of fraction of a millimeter, a tenth of a millimeter or less. So I did do a subsequent calculation, which I'm going to show. And this is a fairly well-known formula. It's a standard leakage equation. Delta P equals friction factor times flow path length divided by the diameter times density times speed squared over 2. That's pretty standard. I'm presuming laminar flow because this leak path would have been a very narrow gap. Again, I'm thinking likely in the section that's glued of the carbon fiber to the titanium ring. And it would have been something extremely thin, under 1/10 of a millimeter, and some amount wider. Let's estimate 1 centimeter to 1 inch, something along those lines. So for such a small diameter, it's going to be laminar flow. The friction factor of any laminar flow path is K, which is a geometry factor divided by Reynolds number. K will vary depending on the geometry. You got anything from 64 from a circular tube, 57 from a square tube, 62 from a 2x1 rectangular path, 76 for a 5x1 rectangular path, and for a rectangle that's extremely wide and thin, you've got 96. From that, you can simply extract from that an equation. I'm substituting the friction factor. This is something that pretty much everyone has done before in many textbooks, but I'll just go over it briefly. So I've substituted F for K over Reynolds. I put what the Reynolds number is, which is density, velocity, diameter divided by dynamic viscosity. You basically crunch through the numbers. You get down to K times dynamic viscosity over 2, length over diameter squared, and velocity. We know that flow is simply velocity times that flow area. And the area of any rectangle is going to be the diameter times the width. So we substitute those numbers, and at any point you can pause this video and look at the math. I don't want to drag it out too long. But you basically get the geometric factor times dynamic viscosity over 2, length over d squared, and then 1 over d times w. All that in parentheses is q. And this part under here is essentially your flow resistance, which I'm giving as the handwritten R. So delta P equals R times Q, where R is your flow resistance. That means the R equals the amount in parentheses. In addition to that, to make it further simplified, I'm going to allow L to be Y times D. In other words, the flow path length, the axial length that the water has to travel through that leakage path, is some factor times the crack gap. So for example, if the crack gap was 0.1 millimeters and Y was 10, then that means that the length was 1 millimeter. I'm going to do the same thing for the crack width. That's some factor times the crack gap. So that the crack width is X times the gap in diameter, small d. So once I substitute those into the equation of resistance, we cross off the d's, they cancel, and you have resistance equals K mu over 2, Y over X, and 1 over d cubed. Now we can infer the crack gap from R, and the reason we can do that is because, as you recall, I've got here this value of Q over delta P, which is the inverse of flow resistance. And because we know this is a fairly consistent number, I've taken the average. The average is about 1.64. So we've got the d cubed is going to equal this when I rearrange d cubed versus the resistance. So in our case, we've got the inverse of resistance is the 1.64 liters per minute per 100 atmospheres. And that gives, I have to convert it to standard SI units, you get 2.7 times 10 to the minus 12th cubic meters per second per Pascal of pressure differential. So you take the inverse of 1 over R to get R. R is then 3.71 times 10 to the 11th. That's how many pascals you need to generate a cubic meter per second of flow through that geometry. I'm going to make a general assumption. These numbers could be anything. I'm going to assume that the axial length of the flow path through the crack is about 100 to 1, 100 times the gap diameter. I'm going to assume that the crack width is about 300 times the gap diameter. The K is going to be 96 because the width is very much wider than the gap diameter. When we plug those numbers in, we get that the crack gap is very small. It's less than 0.04 millimeters. So it's just under half of a tenth of a millimeter. And if we apply these ratios, then you'd have a crack gap of 0.038 millimeters or 38 micrometers by 11 millimeters of width and about 4 millimeters of length. Again, these numbers are just assumptions. You can make them anything you want, but it's not going to change this diameter very much. I played with them a little bit. You're going to get something like 0.05 down to 0.03 because it's because it's the power of third. So it's not going to change it a lot. So in other words, it does not take much. It really does not take much of a crack. We're talking micrometers of width over pretty small subsequent dimensions. We're talking less than ½ an inch wide and about 1/4 of an inch long. And that is enough to generate the leakage rate that we've seen here, which, as we saw, was over 1 gallon per minute at depth of about 3,400, 3,500. And that would have been enough to seal their fate, even had they not imploded. So I'm going to make a last note before I sign off, and that is I'm making the logical assumption that this submersible did not have part of its design in the alarm system liquid detector at the bottom of that crew compartment. Had they had that, it should have alarmed shortly after they first submerged. Normally, a liquid detector is put at the lowest point of any container or vessel where you might not want to have liquid forming. I'm estimating that probably 10 to 15 minutes into their descent, there should have been water detected in the bottom. Had that device been present, they could have easily aborted and come back up at that point. It's very unfortunate that they didn't have that. I understand that submarines do have a bilge water detector. The submersible should definitely have had one, especially given the fact that you're using glue to join the carbon fiber cylinder to the titanium ring so that it can be bolted to the hemispherical ends. Had they had a liquid detector, again, they would have immediately known that something was wrong, that they're taking on water, and they could have surfaced almost immediately, and those 5 people would still be alive. Safety systems should never be shortcut or as a cost savings measure. This is a cautionary tale, not only in the design being of using a material that was not well understood or proven, of cyclical stress of diving and surfacing, that being the carbon fiber. In fact, I may make a subsequent video on that. But something even as simple as you have a seagoing vessel, you need to have a means of determining if you're leaking water in or not. That was something extremely simple to do. The cost would have been negligible. I'm very surprised that that was an oversight. Again, this all presumes that this transcript is correct. If it turns out to be wrong and the real transcript shows them diving at a constant rate, well then that changes everything, because then it means that they were not taking on water. But if this transcript is correct and their rate of water ingress was starting at something and kept increasing as they increased depth, reflected in the fact that their rate of descent kept increasing, then it is truly unfortunate that something as simple as a liquid detector that could have saved everyone's life was absent from this submersible. That's all I have for today. Thank you for joining me, and we'll see you next time.